All right, guys, it's about 10 o'clock. I think I am going to go ahead and just now get started. Hello and welcome to Thursday. I hope that your day is going good so far. Quick reminder that, well, tomorrow I have to go to San Diego, and it sounds like a wonderful thing to do, except that I have to be in meetings for 2 days on Friday and Saturday. So it's a little bit tough for me. I have to go out of town for a couple of days. The homework assignment that you guys are working on, ordinarily I would have made it due tomorrow night, which is my usual MO, which is a Friday night deadline. But since I'm going to be gone, I really actually cannot have office hours on Friday. I am going to extend it till Saturday. So you have an extra day to finish working on the homework that you're currently working on. I've left some room for some problem numbers on the side board over here, but I will point out that yesterday I sent out an email where I explained that some of those problems that are on tomorrow night's homework were already in the videos that you watched and or in the lecture on Tuesday. And this one, for example, is one of them. So if you're looking for help with number 1 from section 4.2, just go back and review. I even, in the email, I even said where you're going to find it. So you just need to go back and look some of those up. But during the break today, if anybody does want to add any other problems to that list, feel free to do that. We're also going to do some more problems from the homework embedded into this lecture also. So I don't think it's going to be that much left over for you to do. But this is an important assignment because we're starting chapter 4 and there's a lot of new ideas here. I think it's really good to take it seriously and try and get off on a good start for this chapter 4, which is a long chapter, admittedly. So that's kind of where we're at. There will be an assignment due on Tuesday as well. That's homework number 10. On that assignment, it's going to be based mostly on what we're going to be doing here today. And of course, on Tuesday, I'll be around. We'll be able to take questions on that assignment next week. So that should help you out as well. So I'm trying to stick with my Tuesday, Friday thing, except that this week I can't, or tomorrow I can't be around. So I'm shifting it to Saturday for tomorrow. Oh, and I will have some office hours on Saturday evening in Zoom and in person. So anytime there's a homework assignment due, I try my best to be around in the evening. So I'll send you an email about that, just so you kind of know when you can ask me some questions. If you don't want to deal with Zoom or office hours, you can also just shoot me your question through email, and I will definitely answer that. So don't worry about it at all. I want everybody to ace the homework, basically. So any questions about any of that before we jump in today? All right, I hope everybody's ready. This is going to be a pretty kind of abstract kind of day today. We are still, we started on Tuesday with section 4.4, and that's what we're talking about here. It's called spanning sets, and I just wanted to point out in our Canvas page, in this folder that has all these documents, these special handouts, I actually typed up literally it's only 3 pages long, a 3-page document called spanning sets to really distill it down to like the bare bones of what you need to know from this section. So if you're looking for some notes that you can just read and kind of get the highlights, you can take a look at that. Of course, there's also a video that I did, like a 30-minute video that's in the videos compilation about spanning sets too. So it's not like there's any lack of information in the Canvas resources. But of course, we're going to do it right now, all together right in front of you here. Since we're all here right now, we're going to talk today mainly about spanning sets. So what was the idea? We started this on Tuesday. The idea was if we take a vector space, and this could be any vector space. It could be polynomials. It could be matrices. This could be a vector space of calculus functions. Whatever it is, whatever your vector space is, we can grab some random handful of vectors out of that vector space. And what we were doing on Tuesday was we said, let's form the span of those vectors. And when we do that, what we're actually doing is we're building all possible linear combinations of whatever that handful of vectors was. So remember that in a vector space, I'm allowed to do addition and scalar multiplication. Those are the two operations. And so what you see here on this second line is just sort of what the general expression would be when you combine together the original handful of vectors using scalar multiplication and addition, right? So this is what we see here. Okay, so you see this expression a lot in linear algebra, guys. C1 times V1 plus C2 times V2 plus C3 times V3. You can just build all of those expressions. And provided that you take all of these linear combinations, then as I explained on Tuesday, what you're really doing is you are closing up under addition and scalar multiplication the handful of vectors that you started with in such a way that it turns into a subspace. Guys, this is the really important punchline here, is that anytime you take the span of anything, doesn't matter what the vectors are, doesn't matter what the vector space is, if you take the span of whatever, right, it will always form a subspace. So let's just remember from last time, a subspace has to be closed under addition and closed under scalar multiplication. And if you take all possible linear combinations of a handful of vectors, you are closing it up under those two operations. So you're making it to be a subspace by doing that. You're actually creating it as a subspace that way. Yes?
By having them be closed by those two operations, do you also include the zero vector check?
The zero vector is automatically going to be one of these linear combinations, because if you take all of the constants to be zero, right? So if you put a zero in front of every single vector, that's included in this set. Well, what is that? That's 0 plus 0 plus 0 plus 0, which is 0. So the zero vector gets captured as one of the vectors that's in this linear combination. So yeah, you don't have to think about the zero vector, right? Which is a good thing to normally, that's a good thing to be thinking about, because if the zero vector is missing, then you do not have a subspace. That was our zero vector check. But when you form the span of a set of vectors, you're guaranteed to have a subspace, which means you're also getting the zero vector in there, right? Let's just practice on an example, a couple of examples here to start off today with. So example one is just asking, well, what is the span of this vector right here? By the way, looking at this vector right here, which is 2, negative 3, can you tell me, just by looking at that, what my big vector space capital V is? Say it again. R2, exactly, because I have 2 slots in this vector. So in this problem, I'm just working with R2. And I wanted to work with an example where we can actually draw a picture of it. So I actually am going to draw a picture of it. And notice that we only have one vector here. So this could be thought of as our V1. And I'm really just taking the span of one single vector. Now, what would that end up being? If you look at the expression for the linear combination here, if you only have one vector, then do you see that what you really just get is C1 times that vector? Right? So in this case, let me just put the solution right here. We don't need a lot of room for this because there's only one vector that you're taking the span of, right? So the span of 2, negative 3 would be equal to the set of all possible linear combinations of that one single vector, which would just be C1 times 2, 3, right? So just, there is no addition needed because I only have one vector, so I'm not doing any adding. It's literally just this. I kind of ran out of room here, guys. I should write this a little bit better. This would be such that, let me see if I can squeeze this in here. Such that, I'll just put it over here. C1 is in the real numbers. Okay, I'll just squeeze it over there like that. Okay, so now what is that actually visually? If I wanted to draw a picture of this, let's actually have a visual of this. Here's my vector space of R2, which is just the XY plane. Okay, and I can plot this vector, which is the vector 2, negative 3. That would just be this vector right here. That's where V1 is. Let me kind of draw a few more tick marks here just to fill out my axes a little bit. So my vector v1 is just this dot right here. It's just this dot that's at the point 2, -3. But what is the span of that one dot? Well, it's all scalar multiples of that vector. So you're taking this vector and you're just going to stretch it or shrink it to any amount that you want, right? Using whatever scalar multiple that you want. What do you think you might get? Visually, what do you suppose it might be? A line. A line. Is that what you were gonna say, Arnav? Yeah, it's a line. It's a line, guys. If you just take this vector and then you kind of, if you multiply it by 0, you'll get your 0 vector. If I multiply it by 1/2, I'll get that vector. If I multiply it by -1, I'll get that vector. If I scalar multiply it by -2, I'll get that vector, or +2, I'll get down here. Basically, all of these dots form a line, and that is your what we would call S, your subspace, which is just the span of that one single point.
So when you apply the scalar multiplication, you know that it's gonna like form that line, which is be part of that subspace, right?
That's it. It is the subspace. The subspace is the line. So if I wanted to describe this in words, right, this is the line. I'll just put it in words here so we have some description of it. It is the line through 0, 0, has to go through the origin, of course, and the point 2, -3. That's exactly what it is. So it is just this line right here. Now, in the video notes, sorry, did you have a question?
Yeah, it was just and the solution is it 2, 3 or 2, -3?
It should be, oh, it should be 2, -3. That is a typo on my part. Thank you for catching that. Yeah, 2, -3. In the video notes that you watched over the last weekend, I had a line in those notes as well. But the thing about that line, I have one in the notes that I think was like this line. But this line does not go through 0, 0. It's missing the 0 vector. So this one was not a subspace. It fails the 0 vector check. But this line does go through 0, 0. And so it passes the 0 vector check. And more than that, it's actually a subspace. Guys, if you add 2 points that are on this line, you will just end up somewhere else on that same line. If I take a point on this line and I scalar multiply it by a constant, it will just move me to a different point on that same line. Right? It does not fall off of this line. So if you're thinking about closure under addition and closure under scalar multiplication, those are definitely going to be good to go. Actually, this is related to one of your homework problems. So before I do example 2, I'm going to take a quick little follow-up. So I can help you with the homework that's due on Saturday. The follow-up problem is actually 4.3, number 2. So I'm going to do this problem with you guys right now. What this problem says is it says let S, in case you haven't looked at it yet, I just want to do it with you. It's the set of vectors X in R2 such that X is equal to 2k, -3k, such that k is a real number. And what the question is asking is, it says in part A, show that S is a subspace. Now, usually when I see that question, the first thing that comes into my mind is, oh, I need to show that S is closed under addition and closed under scalar multiplication. So, if you were trying to do that, I'm not going to do that, but if you were trying to do that, for example, closure under addition, you would take, 2k and -3k, and you would add that to, I don't know, 2l, comma, -3l. You would take 2 points that were both on the set S and add them together, and you'd find out that, oh yeah, the answer is 2 times something, comma, -3 times something, right? So it is in the same form. You would check that off. Okay. So that would be closure under addition. Unfortunately, the book used a K for the notation here. When I do scalar multiplication, I usually use K for the scalar, as you remember from my video notes. So it's not set up so well for that. But guys, I actually have a faster, much more elegant solution to this problem now. I'm crossing it off because I'm going to let you, this is fine, but we have a better way to show that S is a subspace now, right? And I'm even going to let you use it. Technically, it's in section 4.4, and currently we're doing homework from section 4.3, so you probably feel like, that's cheating, you shouldn't be using the next section, but I am going to let you do it right now. Does anybody know what the elegant justification is that S is a subspace? Show that it's a span of something, because a span of something always forms a subspace. That's exactly right, guys. And S actually is the span of, what is it the span of actually? Well, if I pull this K out of the vector and treat it as if it was the C1 that we had a few minutes ago, then it's actually just that exact thing. It's just the scalar multiples of the point 2 comma -3. And then you can just say, which is always a subspace. So that's an elegant way to argue why this problem number 2 from section 4.3 is a subspace. It's because it is expressible as a span. Anytime you take the span of anything, you always have a subspace automatically. So if I can take a look at what they gave me, and if I can realize that, that's just the span of this one point, then I already know it's a subspace. Automatically.
That because like the the K state consistent, so like when you apply the span, it's like you're just treating K as like if it was C.
It's like C1. Yeah, it's just the C1. Yeah, exactly. Yeah. Question.
So going back to that example that we did in the video.
Oh yeah.
So
This one.
How wouldn't have a span?
No, you would not be able to write this one as a span. Yeah, and it's not a subspace. It would fail to be closed under addition. It would fail to be closed under scalar multiplication. Everything would come crashing down, burning in flames on this example. Actually, so if you'd like a really crisp statement about this, if you're talking about lines, a line will be a subspace precisely if it goes through 0, 0, or if it's 3 dimensions 0, 0, 0. Right? So if your line passes through the origin, it's going to be a span, it's going to be a subspace. If it does not pass through the origin, then it fails the 0 vector check immediately, and it's not a subspace. So it's real easy to kind of sort that out. Okay? On part B of this question, it just says make a sketch of your subspace. So part B is to sketch the subspace S, and honestly, that is exactly this picture right here. So you already have your picture of your subspace there. Okay, what do you guys think? Any questions on that? Pretty good. This one's nice because you can actually draw a picture of it, kind of visualize what a span looks like. I'm going to erase this part now so that I can talk about example 2. Example 2 is not going to be quite so nice for pictures, but the concept is still going to be, I think, pretty much the same thing. Let's look at example 2 on my warm-up example here, guys. It just says, what is the span of these 3 vectors here? Now, based on what you see here, does anybody have a proposal what my universe is? Like, what's my big vector space V that we're working with for this example? M sub what? What is N here?
The number of rows.
And how many are there?
3.
3. So I'm going to write M3 of R. That's exactly right. Yeah, so my universe is M3 of R for this example. And here I have 3 specific vectors, V1, V2, and V3. We can label them. Okay? And I'm saying, what is the span of these 3 vectors? First things first, guys, I already know that it is a subspace of M3 of R because it's a span. if I see that word span in front of something, it's already automatically a subspace. I don't have to think about it too hard. But for my solution, this time I can't really draw a picture so easily, so I'm just gonna try to write out what this would be. This would be equal to, so I'm just gonna kind of start solving it down here. All possible linear combinations of those three vectors. So if I wanted to write it as a set, it might be C1 times the first matrix here. Okay, and then plus C2 times the second matrix, which I'm just gonna copy here. And then plus C3 times the third matrix, which is the one I'm drawing right now. So it's just C1 times V1 plus C2 times V2 plus C3 times V3. And this is gonna be such that C1, C2, and C3 are just real numbers. So that's kind of the form of how you would write the expression, okay? Now, what I'm gonna do next to clean this up a little bit is I'm gonna stick the constants inside. Okay, these are scalars in front of these matrices, so I can just filter them into the inside. And then I'm also gonna do the addition at the same time. So you guys ready? This is the key algebra step. I'm gonna put everything inside the matrix. So there's nothing in the upper left corner because that's just 0 all the way across the board. But then if I look at the top middle entry, I have a C1 on this first matrix, okay? The top right entry has a C2. The left middle entry has a negative of C1. The very middle of the matrix is all zeros all the way across the board. The right middle entry has actually a C3 on it. I'll put C3 there. And now I go to the bottom row, same idea. C2 with a negative, right? And then there's in the bottom middle entry, there's a C3 with a negative, and in the bottom right corner, there's nothing. So all I did right there, guys, is simply simplify or add this together. So I just said I'm gonna put those constants inside the slots, I'm gonna add the three matrices together and just get one single matrix. I didn't do anything else besides that. It's just matrix, slot by slot addition and scalar multiplication. And this would be such that C1, C2, and C3 are in the real numbers again. So going from this line to this line, right? Going from the middle line to the bottom line is purely just algebra. Just purely algebra. I'm not doing anything more than that. Looking at what I have down here, does that look familiar? Brandon, what does that remind you of? The 3x3 skew symmetric matrices. Let's actually write that down. This is giving me this 3x3 skew symmetric matrices. Somebody's calling me. We're gonna get to wait. That 3x3 symmetric matrices. And so, guys, this means that those 3x3 skew symmetric matrices, they form a subset of M3 of R. So this is it. Because remember, guys, when you take the span of anything, you always get a subspace. I don't know if you guys remember, we did this one. So I'm just going to ask you to compare with group work 6 part B, I think it was. This we did on Tuesday in groups. I don't know if you remember what the problem was. I basically said, take the 3x3 skew symmetric matrices and convince me that they are a subspace. Now, how did we do that on Tuesday? I'm going to use this board to remind you. I won't write it out in detail. I just want to kind of get it in front of you again. How did I prove that the 3x3 skew symmetric matrices were a subspace on Tuesday? Well, I did it the old-fashioned way. Or you guys did it. I didn't do it. You did it. You did it the old-fashioned way. So, okay, closure under addition. Let's suppose A transpose equals negative A. Let's suppose that B transpose equals negative B. And then most groups I think did this, you then just figure out, oh, well, then I have to figure out A plus B transpose, and you do a little bit of work in between, which I'll skip, and you end up getting negative of A plus B, and then we conclude that A plus B is in S, right? We wrote all that down last time. And then we did something similar for the scalar multiplication, right? Let K be a real number and capital A as above. Okay, you don't need to be writing all this down if you don't want to, because it's already been done on Tuesday in the group work. But basically you just would take KA transpose and you just, big thing you want to do is change that into negative of that same matrix. And so therefore, KA is in S. This is the old way to do the problem, right? If I ask you to show it's a subspace, you're going to check that it's closed under addition and closed under scalar multiplication. When I say old way, I mean 2 days old. It's not that old. Just from 2 days ago, this is how we would have done it. Now we have a really cool way to show the same exact thing, which is that the 3x3 skew symmetric matrices are a span. These are all equal signs, guys. The span of these three specific matrices gives me the 3x3 skew symmetric matrices, so they must form a subspace. Whatever we ended up with down here had to be a subspace because it's a span. This thing over here, guys, that I drew in this cloud thing, right, always forms a subspace. Huge, huge theme today. That's a huge theme right now. Yeah. Okay, so I'm going to get rid of this. There's nothing wrong with this proof, but it's just we don't need to do it this way anymore if we don't want to. Okay. Let's do one more example. I'll call this example 3. We haven't done any polynomials yet today, so let's do a polynomial example. What is the span of x cubed, comma, x squared, comma, x, comma, 1? So this time I'll use some polynomials. First we did an example with R2, then we did an example with the matrices, and now I'm going to do an example with polynomials. We'll try to give you a nice variety here. And I'm just going to do the same thing that I've done on the first 2 examples, which is I'm just going to express what this span is. And all it is, guys, according to it's just this thing right here, linear combinations, all possible linear combinations of those vectors. So that's going to be C1 times x cubed plus C2 times x squared plus C3 times x plus C4. And this would be such that C1, C2, C3, and C4 are real numbers. So this is the kind of the totality of what this span would be. Oh, by the way, I forgot to ask you. Got ahead of myself. What's my big universe on this problem?
R2. No, right.
P3 of R. We're looking at polynomials here, guys. So if you look at the polynomials, the highest power of x is the 3rd power. So this would be P3 of R. And whatever this thing is that we're asking about right now is a subspace of that, right? So it always forms a subspace, and it's a subspace of this big universe. In this case, that's my big universe. So my question is, does anybody know what this thing in blue is? Kind of like here, when I finally got to the expression, I said, well, what is it? And in words, you guys told me, oh, it's the 3x3 skew symmetric matrices. What would we be able to say that this is? There's some nice way to say what this is. Keep in mind that the labels on these constants, I don't have to use C1, C2, C3, and C4. If I wanted, I could just use A, B, C, and D. I mean, it's really the same form, right? So what exactly is that? It's all of P3 of R, actually. It's all of P3 of R. Every cubic polynomial is being captured by this span. If I form all possible linear combinations of these four powers of x, I actually get the entire P3 of R this time. That's interesting, that we can get the entire P3 of R out of that. Now, let me kind of explain to you, like, that's not what happened here. That's not what happened here, because here my universe was all 3x3 matrices, and the subspace was only some of them, only the skew symmetric ones. But on this example, when we took the span of these four things, we got the entire big universe V that we were working in the first place. There's kind of a good news, bad news about that. I'll start with the bad news first. The bad news is that I thought that this whole idea of span was to create new subspaces. And that's how I tried to sell it to you on Tuesday. I sort of said, oh, well, let's see if we can grab a handful of vectors and form their span, and we'll be making a new subspace while we do that. So the bad news here, the bad news part of it is that, well, we didn't make a new subspace at all. We actually, by taking the span of these four particular vectors, we actually created the entire vector space. We didn't get something interesting. Like here, this is a little bit more interesting, right? Within the M3 of R, we created the skew symmetric matrices as a subspace. But over here, well, we didn't really make an interesting subspace. We ended up just regenerating the entire universe V that the problem was a part of in the first place. So we can think of that as maybe bad news in a sense, but I always have to have good news to go with bad news. The good news is that we have actually now figured out how to describe the entire P3 of R, which has infinitely many cubic polynomials in it. We have figured out how to describe it in terms of four things. Only four polynomials are needed to express every other vector in P3 of R. That's huge. This is some wild, big, infinite universe of vectors, right? I mean, we could start writing down cubic polynomials from now until the end of the weekend, and we could have millions of them, right? But we can actually write all of them just in terms of these four. It's like these are the building blocks of the entire vector space. In the same way that, the atoms are like the building blocks of our universe, right? You just think about other real world places where this is important, like DNA is the fundamental makeup of our genetic beings, for example, and people want to study that. They want to understand the foundational things that create the larger universes, whether it's people or whether it's molecules or whatever it is. So these are the basic building blocks, in this case, of that particular vector space. So I actually want to make a definition now. Are we good with that concept?
I was just going to ask, so you're basically saying that when you take the span of all those polynomials, you can express the infinite of polynomials by taking the span of it?
In this case, the entire P3 of R is expressible in terms of these. Which actually, when you think about it, it makes sense. Because any cubic polynomial is expressible or buildable in terms of x cubed, x squared, x, and 1. Yeah. Okay, let's make a definition. When this happens, guys, when we create the entire universe by taking a span of some vectors, those vectors are going to be called a spanning set for the vector space. So I just want to put that in the notes here. So if the span of, let's say, V1, V2, and ... up to Vn, if it equals the entire universe, the entire vector space that we were starting in, if that happens, we call the set of V1, V2, ... up to Vn, we call that a spanning set, that is called a spanning set for V. That is a spanning set for V. And there's another word that you'll hear that's almost the same thing, but we also will say, just as another way of expressing it, using English words, we'll say that this set from V1 to V2 to ... up to Vn spans V. It's just another way of saying the same thing. So those vectors span V in that case. Right. Okay. So that is a very important definition. As you can imagine, that's the title of this section that we're talking about right now, actually. So what I'm going to do is I'm going to now state the two main questions about spanning sets that we are going to care about in this class. Okay. There's two main questions. And by the end of today, I hope that we will have had time. We'll certainly do one of them today and maybe even start the second one. But there's two questions here that everyone in Math 250B needs to be able to do in regards to spanning sets. Okay, this is what I want to kind of quickly go over. The first one is if we are given a vector space V, and I'm going to add here, or a subspace S. So it might be that we have a subspace S, then how can we find a spanning set for V? And then here in parentheses, I'll add for S. So just to go back to example 2 before I've erased it, these three vectors, these three matrices here, are not a spanning set for M3 of R, right? Because the span of these three matrices was not equal to M3 of R. It was something smaller than that. So these are not a spanning set for M3 of R, but they are a spanning set for the 3x3 skew symmetric matrices, right? Because any 3x3 skew symmetric matrix can be written in terms of a linear combination of those three vectors up there, right? So that's kind of why sometimes it might be not the whole universe that we're addressing, but maybe it's a subspace. This would be the S right here. This would be your subspace S that would be within the universe of V. Yeah, Oscar?
Would a matrix or a universe of matrices ever be, like its result, would it ever be a spanning set from the matrices universe?
A spanning set has to be just a list of like a handful of vectors. It's not the entire vector space. So I guess I'm not quite sure if I'm following your question.
So kind of like on example 3, we were able to determine by multiplying by C that through all of that, it would still equal the universe of
Yes.
polynomials. So would there ever be a situation where a matrix would be similar to?
Oh, where that can happen? Oh,
Yeah.
Definitely. Definitely. We're coming to that. Yeah. So, you know, we have an example here that is not a spanning set for M3 of R. Your next question would be, what is a spanning set for M3 of R? How could we find it? You're basically asking the question that I'm asking, which is, if I have a vector space, how can I find vectors that will span that vector space? Yeah, okay, so I'm going to answer this question in just a second, but before I do, I want to get my second question down on the board as well, because this is something else that comes up, which is that given a set, let's say V1, V2, and ... up to Vn, right? The question is, decide yes or no. So this is a yes/no question. Decide yes or no whether this forms, decide whether this forms a spanning set for V. In other words, if I just hand you some vectors, maybe I hand you these vectors, and I just ask you, do they form a spanning set for M3 of R? Now, we already figured out that the answer is no here, but how do we do it in general? Like in a random new problem, if I just grab you a handful of vectors and I ask you, will they span or will they be a spanning set? Yes or no? Will they be a spanning set for the entire universe? Right? That's a question we want, that's a skill we want to learn how to do in this class. How to decide whether we have a spanning set. So just to give you this example that we've already looked at, if I take the set of 0, 1, 0, negative 1, 0, 0, 0, 0, 0, comma 0, 0, 1, 0, 0, 0, negative 1, 0, 0, and then comma 0, 0, 0, 0, 0, 1, and 0, negative 1, 0. So if I take that same set that we were playing with on example 2, this is not a spanning set for M3 of R. It is not. Because when we took the span of those three vectors, we did not get M3 of R, we got just a part of M3 of R, namely the skew symmetric matrices. So that's just a quick example. So if we were asking question number 2 right now, the answer here would be no, that it's not. But then the question number 1 becomes more relevant. Well, how would we find a spanning set for M3 of R? Right, so that's going to be, are we just guess, like here, I just kind of pulled this out of the sky, right? I just took these 4 vectors and said, hey, let's just see what the span is. Oh, it just happens to be exactly the whole universe. But how are we going to sort of methodically produce this spanning set? So I want to start with question number 1 and make sure we're all on board with number 1 first. Okay, is everybody with me so far? I like this stuff. It's a little abstract, but I've gotten a little bit more organized with how to weave my way through this section. It takes a while, but I think over the years of teaching it, I've gotten a little bit more organized. I hope it's making sense. Let's go with question number 1. Yeah, Bishwai?
Wouldn't it make sense to just say that you only, like, for every V, there's only one set that is going to be like that encompasses the entire. Like,
That would be a spanning set? Yeah. So would this be the only spanning set for P3 of R? Or could I have grabbed some different vectors instead? Some different polynomials instead? That's really what you're asking.
Yeah.
The answer is spanning sets are not unique at all. So there could be many other right answers. This is kind of the most obvious one. If I'm trying to express a cubic polynomial, I'm going to need these 4 polynomials to do it. But there will be others that you could use as well. So that's a great question. The spanning sets are not unique. You can have lots of right answers. Yeah. Okay. So how do we find even one spanning set for our vector space or for our subspace? This is what I want to get into. Yes, Stephen.
I had a question building off of that. So would this one have another answer that would be correct?
It would. Yeah, I mean, there'd be lots of them. There's millions of them, actually. I could have given you x cubed, and then x cubed plus x squared, and then x cubed plus x, and then x cubed plus 1. If I had taken these 4 polynomials instead of those 4, this is just a different spanning set for P3 of R. Actually, how do I know that this would be also a good spanning set? Well, because remember that when you form the span of these vectors, it's got to be, you're closing it up under addition and scalar multiplication. And so if I take, so if I take like the second one minus the first one, By the way, when I say minus, that's really addition with a -1 scalar in front of it. But if I take the second one minus the first one, that's just x squared. If I take the third one minus the first one, that's just x. And the fourth one minus the first one is just 1. So using these 4, I can regenerate these 4. And once I've got these 4, boom, I've got the whole P3 of R spanned by them.
But essentially, it all comes back just to that.
Yeah, it does. I mean, this is the easiest spanning set of all. So if you have other sets that are given to you, it makes sense to kind of think about them in the context of this. So for example, if I had given you, well, let's just take this one away. If I had only given you these 3 polynomials, you'd look at that and say, oh, well, there's no x squared there, right? So, but x squared is a really important part of writing out a cubic polynomial. So if I'm only allowed to work with these 3 things, I can add all day long and I can do scalar multiplication all day long, but I'll never be able to create an x squared. You guys with me on that?
So then it wouldn't equal to the.
It wouldn't be a spanning set for P3 of R. By the way, is it? This is just a side comment. I should have said this earlier. Is it possible to just say, well, x squared is a scalar multiple of x because it's just x times x? Is that legit? So this vector being multiplied by this would create this vector. But what am I doing right here? Am I doing addition and scalar multiplication? I am not, because x is not a scalar, right? X is actually a vector. And I mentioned this about vector spaces. You cannot multiply vectors together. So this is an illegal operation if we're in the world of vector spaces. So I cannot make x squared out of x. Okay, I see people do that sometimes. It doesn't work, right? You have to just keep scalar multiples. That means a constant times x. That you can do. But x times x, that's no longer a scalar times a vector. Anyway, let me get back to this. Okay, what is the answer to question number 1? How do I find a spanning set for V? It is a 3-step process, and I'm going to lay them out right here. And then we're going to practice them. The first step is to write the general form of a vector in V. And over here again, I'm going to put in parentheses for S. If it's a subspace instead of the whole universe, if it's just a subspace of the universe, then we can write it like that. Oh, and then using variables. So I write the general form of what a vector looks like. Okay, we'll do an example in a minute. Let me just get the whole list down first. The second step, which I'm calling step B, is something I will be referring to a lot called bust out the variables. And I've been looking over my students' shoulders over the last few years. Students seem to like to abbreviate this BOTV. Bust out the variables. Okay. And then the third step is to make a list. This is the last step. Make a list. Now, why am I making a list? Well, it's because I'm finding a spanning set. A spanning set is a list. It is a list of vectors. So make a list of the vectors left behind. Make a list of the vectors that are left behind. So I would like to do some examples of this. So here is an example. Find a spanning set. Find a spanning set for, I'll call it S. So this is actually going to be a subspace. And I'm actually going to go back to a concept from the last day or two. I'm going to make a null space of a matrix here. So let's make the matrix 1, 2, 3, 4. And then on the second row, 5, 6, 7, and 8. I'd like to do this example. So let's see, first of all, if people remember from the video, this null space is a subspace of some universe. Can somebody tell me what the universe is that this null space is a subspace of? Like where does the null space live in terms of the big universe?
Is it
It does not start with an M. It's very tempting because it looks like it's a matrix. What did you say? Or somebody said it.
I was gonna say M.
It is Rn. It is Rn. Do you guys remember from my video? The null space of a matrix is always a subspace, and it's a subspace of Rn. Now, in this example, what is the n here? Like, what's the size of this matrix? 2 by 4, and the n would be what? 4, right? So this is a subspace of R4, just so we have that in the background in our mind. And I would like to find a spanning set. Okay? Yes.
I have a question. The book, it also says it's CN. So.
Oh, that's for complex numbers.
Okay.
I'm not gonna do that in this class. Yeah, no worry. Subspace of Rn, right? So it would be a subspace of R4. What that means is that my null space should have 4 slots in it. And in order to find a spanning set for it, the very first thing we actually have to do is figure out what is the null space. Like, let's actually calculate the null space first, and then we'll find a subspace for it. And this is certainly good to practice as well. So I'm going to start by just finding the null space. To do that, I hope everybody remembers from the video how the null space works. You basically just take your matrix and you augment it with a column of zeros on the right side. I'll circle this pivot here in the first row. And I need to get this into row echelon form. So I actually am going to do an ERO here, which is going to be A12 of -5. So I'm going to leave the first row alone because it's kind of good to go. And I'm going to take -5 times the first row, and I'm going to add it to the second row. Now, guys, I'm going to go fairly quickly on this. I don't want to get too distracted by the EROs anymore. But I take -5 times everything on the first row, and I add those results to the second row. So I should end up getting something like what I have written there. The second row is 0, -4, -8, -12, and 0. And then I'm going to multiply row 2 by -1/4 so that I can create my pivot in that second column. So if I multiply the second row by -1/4, I'll just get 0, 1, 2, 3, and 0. And there's my row echelon form. Okay, so there's your first part of the problem, is to just figure out what the row echelon form is. Now remember that a null space, there is a system of equations running in the background. That's why we have this set up the way we do. So there are unknowns here. Even though they are not mentioned in the given problem, I'm going to introduce those unknowns as x, y, z, and w, like we often do. Which of the variables would be free variables here? The z and the w, right? Those are the ones that don't have pivots. So I'm going to call z equal to r and w equal to t. These are the free variables. And then what I have to do is I have to back substitute, going from the bottom upwards on the matrix. I have to back substitute into this matrix. Okay, so take a look at the second row here. The second row is y plus 2z plus 3w equals 0. If I think of it as an equation. And so I can solve for y. I'm going to put that over here. Y would be -2r minus 3t. Okay, so I'm just taking this one here, guys. It's this little equation here. I'm solving it for y. So I isolate the y, and in terms of z and w, we can then just replace in terms of r and t. Okay, and then from there, I have to go back and figure out what x is using the first row. Maybe I'll scribble over here for a second. So x plus 2y plus 3z plus 4w is supposed to add up to 0. I want to solve that for x. So if I solve this for x, I have to move everything to the other side of the equal sign. So x would be negative of 2y minus 3z minus 4w. And I need to replace all of that in terms of my free variables r and t. So the y needs to be replaced by negative 2r minus 3t. And then the z gets replaced by r, and the w gets replaced by t. So you end up with this for x. I need to simplify that just a little bit if I can. It's actually 4r minus 3r, which is r, and 6t minus 4t is 2t. So let's put that down as our x variable. Okay. Give you guys a chance to catch up here. I'll erase for a second. By the way, so far, everything that we're doing on this problem is chapter 2. There's no new material in anything in blue here. This could have been on your midterm last week. I could easily just put that there. It's the same thing as solving a system of equations. But what is the null space of A? Let's write it down. I'll put that on this sideboard over here now, guys. The null space of A. You guys know how to do this as well. This is old skills that we're just reviewing. We just make a list here of the slots. So x is r plus 2t. Y is minus 2r minus 3t. Z is r. W is t. And this is such that r and t are real numbers. Right. Everything up to this point is a chapter 2 problem, just solving a system of equations. I have found the null space of my matrix. It's that. But the question is asking me to find a spanning set for it. And I've got my 3 steps up here to finding a spanning set. What does step 1 say? Write the general form of a vector in this case, it's S. Write the general form of a vector in S. Well, guys, guess what? That's exactly what this is. This is right here. This is what I'm calling step A. Step A is to just write down that general form. Okay, you just write that down. And so all of this work in blue is just leading me to step A, to write down the form. Okay. The next thing we need to do is do steps B and C. So step B, here we go. This is where it says bust out the variables. What in the heck does that mean? I'm just basically going to factor out the variables that are in this general form. Notice that I've used the variables R and T for this example. So I'm just going to bust them out. Well, what does that mean? I'm going to basically take this expression. Let's just go ahead and put an equal sign here. I'm going to factor out. When I say bust out, I just mean factor out. So you take the R, that's one of your variables, and you're factoring it out. And what is left behind? Well, there was a 1 in front of the R here. There was a -2 in front of the R here. There was a 1 with that R, and the last slot doesn't have any R's at all. And then to that, we are going to add another term that corresponds with T. So now I'm going to bust out the T. The first slot has 2 T's. The second slot has -3 T's. The third slot has no T's. And the fourth slot has 1 T. Yeah. I am going about as slow as I can go. But I will pause and let's take a look at that. If I bust out the R and the T, that is what you would end up with. So you're essentially factoring out whatever the variables are that you had written in the general form. Does that make sense? That we're gonna practice this. Of course, if I was working in a universe of polynomials, it would look totally different. If I was working in a universe of calculus functions, it would look totally different. It really depends. In this case, we have 4 slots. We are working, after all, in R4. Remember, the universe, the underlying universe here is just R4. I saw somebody had a hand up over there. Yeah.
Yeah, I just wanted to confirm, like, if we didn't have 3 variables, you'd be factoring out like 4 variables, right?
If you didn't have any free variables.
Yeah, like if you're working with X, Y, Z, W, then you'd be factoring out X, Y, Z, W, same thing, right?
And you get 4 variables out of that, yeah. Well, okay, so I don't wanna spend too much time on this, but if I asked you for a spanning set for R4. Step 1 says write the general form of a vector in R4. Well, for that, you would write down, something, maybe you'd write it like that. That is the general form. For something in R4. Now you bust out the variables. Okay, you pull out the A, and then you pull out the B, and so on, right? And you're getting, so this is the next part here. What does step C say? Step C says just make a list of the vectors that are left behind, and that is what I'm going to do right now. Is I'm going to write down the spanning set is it's a set. And specifically, you just write down the vectors that are left behind right here. So that's the first vector, comma, and then the second vector 2, -3, 0, and 1. Yeah, that's your spanning set. That is the spanning set for the null space of this matrix. If I wanted a spanning set for R4, I would have done this. And how many vectors would I have gotten here? 4, right? Well, does it make sense that a subspace of R4 should require less vectors to span it than the whole big universe? Somehow the number of vectors that you are writing down here is going to be important. The more vectors that you need in your spanning set, the bigger that particular subspace is. Yeah, so in this case, I only needed 2 to span the matrices there. Okay, so far so good? Let's do another example. And then we'll do one more example, then we'll take a little break. But I want to do something with polynomials. We're still on question number 1. Haven't gotten to question number 2 yet. But we're going to get to question number 2 after the break. So let's do another example here on question number 1. So I'll just call this example. Find a spanning set. Find a spanning set for S, which is going to be the set of polynomials. So I promised a polynomial example. Let's call it P of X, which is an element of P3 of R, such that P of 5 is equal to 0. This time, I'm going to have to ask you to take my word for it that that's actually a subspace. I didn't have to have you take my word for it here because we proved in the video notes that a null space of a matrix is always a subspace. So that was not a question. Guys, you can't find the spanning set for something that's not a subspace. It doesn't make sense. So this thing that's S is being labeled as has to be a subspace or the question doesn't even make sense, right? So this one, if you really wanted to show that this was a subspace, you would have to check that it's closed under addition and closed under scalar multiplication. The stuff we were doing on Tuesday. Okay. Not going to do it here, but just take it for my word for it that this does form a subspace. By the way, subspace of what? Yeah, it says it right here, actually, the P3 of R. Exactly. So this is a subspace Exactly right. It's a subspace of P3 of R. That's what we have here. Okay. So of the 3 steps that are on this process that we're learning right now, the hardest one is step A. You can even see that if you look at how much work on this last example, how much work went into doing step A compared with step B or C. Once you get this general form written down correctly, steps B and C are really straightforward. They go just one line by one line. But we have to get the general form of a polynomial in S written down right now. So I'm going to start doing that. So this is going to be step A for the solution. Would somebody like to propose what the form to start with should be? Oscar.
Could it be x cubed plus x squared plus x plus 5?
It has to have variables in it.
Oh,
Using variables, so I have to hear A's, B's, C's. I have to have letters into it.
so like a cubed or ax cubed, sorry.
Ax cubed
Plus bx squared plus cx plus d.
something like that. So, I always like to get my students participating in class, so I don't like to make anybody feel like they shouldn't give an answer. This is the popular thing for people to tell me. And the problem is that it is not correct, as it turns out. This one is not correct, but this is what a lot of people would tell me. The reason that this is not correct, this is the correct form for a polynomial in P3 of R. But this form that's written down here completely ignores this condition. It's not incorporated into it. So what we have to do is we have to incorporate this condition into this form. This is a good starting point. It's absolutely a good starting point. But guys, watch this. I'm going to plug in 5 into this.
Be a5x cubed.
I'm going to put in 5 for x right here. The x is the input. Put in 5, I get 125a plus 25b plus 5c plus d. And the condition is that it should be equal, I'm going to set it equal to 0. So the point being that when I plug 5 in for x, I'm supposed to get 0. That actually creates an equation here involving a, b, c, and d.
Just the part of a question.
We're still on step A. Yes, this is all step A. I'll let you know when we get to step B. Now this is like a system of equations that you would want to solve, except that there's only one equation. So I can put it into a matrix, is what we always learn how to do. It only has one row though. This matrix would only have one row, which is just that one row right there. And my unknowns, at least with the setup I have here, would just be A, B, C, and D. Okay. And, so this is where my pivot will be. And essentially you have 3 free variables here, guys, which are B, C, and D. I think I'm just going to leave those as my variables. I won't change them into the R and the T and the S like I sometimes do. I'll just leave them as B, C, and D. And then what I have to do then is solve for A in terms of the free variables, just like what I was doing over there on that example. So I have to solve for the A. Let me do it right here. That means I have to move everything to the other side of the equal sign and then divide by 125. Can I do that all in one step? Subtract everything to the other side and then just divide by 125. So if I did that, I would have negative 1/5 of B, and then minus 1/25 of C, and then minus 1/125 of D. Right, that's the form of A. That's solving for A. So if you solve for A, that's what you would have. So the actual form that you need here, guys, the actual form that you need for your P of X, I'm still on step A. Still on step A. I have to take this A and put it in right into here. So P of X becomes negative 1/5 of B minus 1/25 of C minus 1/125 of D, all of that times X cubed. And then plus BX squared plus CX plus D. And my friends, that's actually the form that we need. So if we just left this as the form, let me just pause for a second. If we left this as the form and then we busted out the variables and then we made our list, guess what list we would get for this? If we used this to bust out our variables from and make our list, we would just get x cubed, x squared, x, and 1. Which actually was the spanning set for the entire P3 of R. And that's not what S is. S is not equal to the entire P3 of R because we are only looking at polynomials that give you 0 when you plug in 5. And that's a smaller number of polynomials. Right? So this is actually the form that you need. Are we okay with this? This is the key. This is most of the work is here, guys. Steps B and C are going to be one line, just like they were over there. So let's write it down and then we'll take a short break. Step B, I'm going to bust out my variables. That's step B, bust out the variables. Keep in mind, guys, X is not a variable. X is part of the polynomial. It is an object in this context. The variables that I'm speaking of here, bust out the variables, I'm speaking of the B, the C, and the D. If I bust out the B, I'm going to scan this expression from left to right. Everywhere I see a B, I'm going to see what it's multiplied with. The first B is right here. It has a negative 1/5 and an x cubed in it. And there's also a B over here, which has an x squared on it. So I factor the B out of that part of it. And then I'm going to do the same thing with C. So everywhere I see a C, I'm going to factor it out. There's a negative 1/25, and then there's still an x cubed for that term. And I also have a C right here. When I bust it out, it leaves me with x. And then lastly, I have to bust out the D. When I bust out the D, I get negative 1/125 x cubed plus 1. That's it. Yes, Kim?
So for this side, when you bust out, why the comma on this side of us?
So here I have commas. Is that what you're talking about?
Yeah.
Is because this problem was living in the universe of R4. And the vectors in R4 are drawn out with slots. This universe is, we're looking at a subspace of P3 of R. When you're working in the universe of polynomials, you don't have commas. You have powers of X that are being written down. So the notation looks a little different, but what I'm actually doing is the same in both problems. Let's make our list, guys. Let's get our final answer here. The spanning set. Sorry, I'm going to write this down here on the bottom. Let's get our big curly braces out. What does step C tell us to do? It just says make a list of the vectors that are kind of left behind. So that's just the things that are being multiplied by the B, the C, and the D. So I'll get negative 1/5 of x cubed plus x squared, comma. So now I'm making a list so I can put those commas there, Kim. So I have that one, and then I have negative 1/25 x cubed plus x, and then comma, and then negative 1/125 x cubed plus 1. That's my spanning set. How many vectors are in my spanning set? 3, right? 1, 2, 3. Does it make sense that it should take me less vectors to span this one than the P3 of R as a whole? If you remember the P3 of R, that was the big universe of all cubic polynomials. That took 4 polynomials in order to be able to span it. Believe it or not, this is a subspace of that. It's smaller. It is smaller than P3 of R because we now have a condition that only some polynomials will meet. And so this is actually a smaller set, and that's being reflected in having less vectors in my final spanning set. It takes less vectors to, admittedly, they're not as nice, but there's fewer of them. There's fewer of them because my subspace is smaller than the big universe. The other thing, I don't know if anybody's stopped to check it yet, but if you plug 5 in for X into any one of these, I promise you, you will get 0. You have to get 0. These are supposed to be vectors that satisfy this condition. And so these polynomials accomplish that. If we just took these polynomials, you plug 5 into these, you don't get 0. These polynomials are not in S to begin with. But these 3 polynomials, they are. They absolutely are. The hardest part of this is step A. Just getting the form of the vector written down. And Oscar started us off on a great note with this cubic polynomial here, but I had to tweak it a little bit because this P of 5 equals 0 forced me to actually use this as the form of the vector in this step A. Yeah, okay. Guys, let's take a little break. I think we have got a lot to chew on here, so I'll give you guys a few minutes to stretch your legs. And then we'll pick it up from there. And in the meantime, there's a few people who I think didn't get their exam back. Brian. Oh, that's right.
After we, so basically like we're gonna be.
Okay.
By like certain grade.
Anybody else here didn't get their test back yet?
You saw like. Right now, I don't think there's something that. Hey, dude, I was watching that video about like that homeless stuff like the situations from like from like MIT from like 16 years ago. So it's pretty cool.
What's the, who was it?
It was all over, dude.
I was watching, is it from those Oxford?
Oh, really?
Yeah, he's like, it's only a chalkboard.
Yeah, I'm not.
This professor. Imagine it looked like on a video and like everything's. Oh, like they're like. Great body, small build.
Thank you for letting me know. I'm so sorry.
Independent faces, international.
Yeah. Glad you're back.
Bro, it's funny because I heard, I think this actually when I was born. But back then I was like a like, actually,
Mhm.
you know.
I was normal, but I'm looking
Okay,
for.
oh, you said that you were normal?
It's in the
Oh.
website.
Nice, I used to play Minecraft like, I don't know. Is that a little?
Yeah. You should have brought it home.
It's like
I
back
could
in,
read a little harder.
I like it anyway.
Was it never been again?
Yeah,
I think it did not.
dude, me, but it's like on your dash. We just got told that there's a potential that our physics professor, that she's not gonna give us practice exams. Like, there's a major.
Was it physics 6 and 7?
Yeah, it was really like, oh my.
As you need it, brother. Just things.
The fraction,
Ask chat people. Be overly specific with the prompts.
you know how many slides she has, like, after, like, 6 weeks or 5 weeks?
Well, that's all right.
Yeah, like 200 something.
I can eat for like.
You know, like, why can't we change the problem?
You guys have parents?
We're living in the universe of like, on forward. Like, is your subspace, wasn't, you know, make the argument that it's gonna be half every time.
What do you?
Because earlier we did this, where it was, we ended up with these two sets.
Mhm.
Well, it's like two, horizons.
Oh, I know what you mean. No, because the other, there was, Anthony.
Was that
R
R4?
four, and then, you know.
Well, because this was R4,
Mhm.
and we finished with two.
Yeah.
But what are these other, before we're ending, we used to start with one.
We have. Yes.
Professor, one of the problems, we were working in the universe of R4.
Yeah.
And we ended up with two vectors in our spanning set.
Yeah,
Could
but
you-
R4 refers to how many slots there are in each vector.
1, 2, right? Oh,
Or,
2, 3, 4.
so that's two vectors in R4.
Would you say that, like, if you're working with the universe of 4, that you're always gonna end up with 4?
Well, not necessarily 4 vectors, but you should have 4 slots in the
Four
vectors
slots.
in that universe, yeah. Guys, I thought I would pull up another of the problems from the homework assignment and do it with you. Whether you've looked at it yet or not, I think it's a good problem, so I'm gonna work on it with you here for a second, because I can tie it in nicely to what we've just been talking about. That's why it kind of fits well here. So this is number 12 in section 4.3. So just take, if you haven't done this one yet, just take some notes on it and then be sure to study it before you submit it and make sure you're comfortable with it. What they're doing in this problem, in this whole section 4.3, is they're giving you a vector space, and then within that they're giving you a subset S, and they're asking you whether it is actually a subspace. So the vector space here, the universe, is the M2 of R. And the set S that we're looking at are the 2x2 matrices where all of the entries add up to 0. Well, that's the condition that's kind of being thrown at us here. All of these entries sum to 0. Okay. And by the way, it's very important that that is a 0 there. If they change this to a 1, okay, you don't need to change it now, but I will change it for a moment. If that becomes a 1, then all of a sudden your 0 vector check would fail, because if you add up the entries of this matrix, you don't get 1. Okay, so but luckily they put 0 here. Okay, so that gives us some hope that this is going to work. So the 0 vector check would pass if I have the entries adding up to 0. So we could go into checking if it's closed under addition and scalar multiplication. And that's the way section 4.3 would probably have you do the problem. Check that it's closed under addition and scalar multiplication. But I'm going to show you a different way, and you're allowed to use this way when you turn it in. We'll take full credit for this one, okay? Which is, I'm going to try to show you that the answer is yes. And I'm going to try to show you that it is a subspace by producing it as a span. Because remember, anytime you take the span of anything, you always get a subspace. So if it's going to be equal to the span of something, then I have to actually figure out spanning set of what. It's a span of what. So to solve this problem, I'm actually going to kind of go through my 3-step process from question number 1 from today, which is if I want to find a set that spans S, I should do these 3 things. So the first step is to write down the form of a vector in S. Can somebody help me with that? How could I write down the general form of a 2x2 matrix whose 4 entries add up to 0? I'll call this step A. My grader won't have any idea what that's talking about, but that's okay. If he grades this one. So what would be a form for a 2x2 matrix where the 4 numbers add up to 0? And keep in mind, you're going to be using variables. Anybody want to give it a try?
Can you do 2 matrices, right? The sum of 2 or just
I just want one matrix.
1 matrix?
I just want one matrix here, and just what would the form of that matrix have to look like to start filling it out using some letters. I mean, suppose that somebody on the street comes up to you and says, "Can you give me a matrix where the 4 numbers add up to 0?" It's probably not going to happen. But if you're feeling a little pressured by that, you might say, "Oh, I can put any number here I want. I can put any number here I want. I can put any number here I want, as long as I pick the last number so that it cancels out what I've added up to so far." So did you ever catch what I just did there? I said anything here, anything here, anything here, and then the last slot has to cancel out all of the other 3 numbers, because this says the entries sum to 0. So if I want to put that into general notation, you want to try it?
You can do A, B, and C.
A, B, C.
Add up A, B, and C and put a negative on all of them.
You got it. You got it. You just take A, B, C, and then the negative of all of those, and that's actually the form. Okay. Let's go to step B. Step B says bust out the variables. So I'm going to factor out the A, the B, and the C. So if I factor out the A, I get a 1, a 0, a 0, and a -1. Okay. So there's an A in the upper left corner, and there's a -A in the lower right corner. So that's what happens there. When I'm doing the A part, I don't even think about B or C. I'm just looking at where is the A, right? And then I add to that another term that goes with the B part. All right, there's no B in the upper left corner, but there's one B in the upper right corner, nothing in the lower left corner, and again, a -B in the lower right corner. And finally, I do the same thing one more time with C. Nothing on the top row has C in it, and on the bottom row, I'd have a 1 and a -1. Okay? That's it. That's busted out exactly like you want it to be. And step C is to make your list, right? So your list would be the set of, and now you just grab the matrices themselves. Notice that when I'm making these lists, I don't have the A or the B or the C in the list, just the vectors themselves. So 1, 0, 0, -1, and then 0, 1, 0, -1. And then the third one would be 0, 0, 1, and -1. That would be it. What I've just written in these braces is a spanning set for S. By the way, if I wanted a spanning set for V, I would have had to start off with 4 letters, right? If I wanted just a generic 2x2 matrix, I would have had to start off with 4 letters. And if I had busted that out, I would have gotten 4 matrices in my spanning set. This is just like on the last example. The subspace is smaller than the original vector space. So why is the answer to this question a yes? It's because if I take the span of those 3 matrices, that is what S is. So S is the span of those vectors. And a span of anything, I'm a broken record. Anytime you take the span of anything, it is always a subspace. So this is why we have a yes here.
I understand everything you did, but the only thing that I was confused about was the bottom right. Like, why is that? Why are you writing the -A plus B plus C?
Yeah, because I've got to make sure that whatever the form of my matrix is captures this requirement. And to do that, I have to have that last entry cancel it out. Now, somebody earlier today, I forget who it was, asked me if this answer would be unique. In other words, could there be more than one spanning set? Well, imagine that instead of starting off with step A this way, what if I had decided to do this? A, B, C, and then negative of A plus B plus C like that. Actually, this is also correct. It's not the same form as what I gave in step A in blue over here. This would have been correct, but it's different. And when you bust out the variables here, you will not get the same 3 matrices anymore. So you'll get a different spanning set. So this is A-OK, and you can imagine there'd be others as well, right? There could be many different ways to express the form of the vectors in the set. So let me ask you another question. As long as we're playing, this isn't part of the homework anymore. I just want to ask you, so this would have been okay. What about this? What if I did A, -A, B, -B? So we're looking at 2x2 matrices whose entries add up to 0. So I would look at this matrix, I say, yep, the entries do add up to 0. So would this be okay? It would not. It would not be okay. The problem with this one, so this is not okay. The problem with this, guys, is it's imposing too much conditions. This one is actually telling me that each row must add up to 0, which is a different condition than saying that all of the entries add up to 0. This is too specific. It's not general enough. Notice this says general form, right? This would not be that, it's not that this matrix isn't okay as being in S, but it's not the general form of a matrix in S. See what I'm saying? So you have to, it's tricky. You've got to you have to incorporate the conditions, but don't incorporate too much. Like don't over impose conditions that are not assumed. Yes, go ahead, David.
You said it's being too specific and implying that if you're adding up the rows, it equals 0.
Correct.
If you had a negative a like in the diagonal.
If I did this,
Yeah, that's what that's.
C or something.
Yeah.
This would still not work because these would be matrices whose main diagonal adds up to 0. Or even if you change this to a negative b. Right? So now all 4 entries add up to 0 again, but it's too specific because now you're saying, oh, as soon as I put 17 there, I have to put negative 17 there. And as soon as I put 8 there, I have to put negative 8 there. This is not generic enough. It's too specific, right? So if this is the condition, now be careful because I think there's a problem in the homework that says matrices whose rows add up to 0. So if it says that, then yeah, you would need to, make sure that as you go across each row that they add up to 0. We'll practice this next week in some group work as well, but just wanted to point out that really the crux of this matter, guys, is getting the general form of the vector written down correctly. We've seen that kind of in all of these examples so far. So far, so good? Yeah, Oscar.
Just really quick.
Yeah.
I don't know how to go into that, but
Yeah.
the question that you're referring to right now wasn't the lower or higher triangle?
No, this is not about triangular matrices. This was problem number 12.
Yeah.
About the entries that add up to 0. But I know what you're talking about. There's an item asking you whether, the set of upper or lower triangular matrices, I forget what size it was. The 2 by 2?
2 by 2.
Yeah, 2 by 2 matrices. They gave you this set here. And they asked you whether that is a subspace of the M2 of R. Anybody think they know?
It's not.
It is not. You're right. It's going to fail to be closed under addition. And the reason is, well, you have to give an example. So you have to give me, 2. So for your solution to this problem, and I forget which one it is, but when you're doing the upper or lower triangular matrices, you need to give me like a specific matrix. So I could make a triangular matrix like that. That's upper triangular. So that's in S, fine, right? And then I have to make another triangular matrix, but the trick to doing this problem is to make your second example lower triangular instead of upper. So like if I did 4, 0, 5, 6 or something like that. Now this is lower triangular. Oh, that's fine. That's in S because S consists of the upper or the lower triangular matrices. But then when you add these together, so you guys should make up your own example so my grader doesn't fall asleep when he's grading them. But basically, you add these together and you get something that is neither upper nor lower triangular anymore. It fails to be closed under addition. So you just need an example, right? When something like that fails. Okay. I would like to spend the last 10 minutes looking at this question. It's a different question. It's a different question. Instead of coming up with a spanning set, I'm going to give you some vectors and ask you whether they are a spanning set or not. So let's take an example of this for question 2. So now I'm moving on to question 2 that I posed earlier today. And I would like to just show you an example of this. So maybe I ask you this question. Is the set of 1, 1, 3, and then 2, negative 1, 4, and then 3, negative 3, 5, is that a spanning set for the vector space of R3? I can see that these are vectors in R3, and I've got 3 of them there. And the question is, would they be a spanning set for R3? Let's just remember what that means. To be a spanning set for a vector space, what you're saying is that every vector in R3 could be expressible as a combination of these 3. That's what spanning set is. Right. A set of vectors is a spanning set if, when you take all possible linear combinations of these vectors, that you can make any vector in R3. I'm going to show you. I'm going to try it. We'll do this one example, and that should give you the whole procedure for how it always works. Basically, what you're going to do, guys, is you're going to take a random linear combination. I'm going to use, instead of C1, C2, and well, maybe I should use the C1, C2, and C3, because those were the letters that I was using when I wrote down linear combinations earlier. So C1 times the first vector plus C2 times the second vector plus C3 times the third vector. I'm going to set up, this is the form of a linear combination of those vectors. The question is, using this expression, is it possible, I'm going to put the word try next to that, I am going to try to be able to express any vector in R3 in that form. Now, any vector in R3, guys, is just, 3 random values. It would be an X, a Y, and a Z. Now, what you can see here is that although this looks, so the question is not what is the solution for the constants. The question is, can we solve this? Can we solve it? So given the X, Y, Z, which is in R3, can we solve? Can we solve? This is yes or no. I'm just reminding you, it's a yes/no question, right? Can we solve for C1, C2, and C3? Mathematicians are on the receiving end of a lot of jokes involving scientists and engineers and all this stuff. And, it's been said that if a mathematician is sleeping at night and they suddenly wake up and their house is burning down, that they're sleeping in, that they'll say, yes, there's a solution to this. And then they go right back to bed. They don't actually want to solve the problem. They just want to know, can we solve the problem, right? Can we solve for whatever the unknowns are? The engineer is busy putting out the fire, right? And the physicist and all that. But the mathematician, he just wants to know, would I be able to solve this problem or not? Okay. Yes or no? Then they're happy. So anyway, that is the question. Can we solve this problem? Actually, this equation, guys, it might look to you like it's one equation. This might look to you like one equation, but I would like to convince you right now that it is actually 3 equations. Because there is a left slot going all the way across the formula. There is a middle slot going all the way across the formula. And there is a right slot going all the way across the formula. Let's write down the 3 individual equations here, guys. Left, middle, and right. There's 3 of them. If I just look at the first slot, the left slot, I have a C1 times 1 plus 2C2 plus 3C3 is equal to X. That's the left slot of every single thing I see up on that equation. Now, if I do the same thing in the middle slot, I have C1 minus C2 minus 3C3 equals Y. And then if I go to the right slot, I have 3C1 plus 4C2 plus 5C3 is equal to Z. And what do you know? This looks like a system of equations that we could put into an augmented matrix. I'm going to do that. So I'm going to put 1, 2, 3 augmented with X, and then 1, negative 3 augmented with Y, and then 3, 4, and 5 augmented with Z. That's my system. My unknowns are the C1, the C2, and the C3. And what I have to do now is my EROs on that system. Yeah, so I have to quickly get this into row echelon form. I'm going to do it quickly. So I've only got a couple minutes here, and I've got to get to the punchline of this. So I would have to do some EROs. Again, I'm not actually trying to solve it. I just want to know, can I solve it? Can I solve it? So let's do EROs on this. The first row is good to go. 1, 2, 3 with an X over here. On the second row, I need to take the negative of the first row and add it to the second row. So the negative of the first row added to the second row would give me 0, negative 3, negative 6, and Y minus X. So that's A1, 2 of negative 1. And then I'm also going to do A1, 3 of negative 3. So negative 3 times the first row added to the third row is 0, negative 2, negative 4, and Z minus 3X. Just write it like that. Yeah.
I can't really see that, but you're adding row 1 and 2 by -1.
Yes. And then I'm adding row 1 to row 3 by negative 3. Yeah. And then I'm actually going to just simply do A2, 3 of negative 2/3. So you can see I've got a negative 3 and a negative 2, and I want to get a 0 below because I'd like this to be a pivot, essentially. So I'm just going to use negative 2/3 of the second row and add it to the third row. When I do that, the first row stays the same. The second row stays the same. But the third row, if I take negative 2/3 times the second row, if I take negative 2/3 times the second row and I add it to the third row, I'm going to get 0, 0, and 0, and some kind of a mess with X, Y, Z. Do I actually care what the mess is? No. In fact, if I circle my pivots, this is some mess. I'm going to draw a number symbol on that. That is a pivot in the far right column. And what do you know about your system of equations when you get a pivot in the far right column? It has how many solutions? 0. No solutions. There is no solutions here. And when I say no solutions, I mean no solutions for C1, C2, and C3. Can I solve for C1, C2, and C3? The answer is no. And so because of this pivot being in the far right column, the answer is no. Now, can I make a couple of I know I'm out of time, but I have to show you something really cool. I'll be really fast. First thing, do you guys see these 3 vectors anywhere in the matrix? 1, 1, 3, 2, negative 1, 4, and 3, negative 3, 5. Guys, that always happens like that. You do not need to spend your time doing any of this ever again. You can simply take your vectors that were given and go straight to this matrix. That's my first point.
I thought the same thing. I was like, well, why is it doing all that? Isn't it just going?
It's just going into the matrix. I just have to show it to you once so you see it the first time. But starting on next week, I'm gonna take my vectors. If I ask you this question next week, I'm gonna take whatever the vectors are that were given, I'm gonna slam them into the columns of the matrix immediately. One more comment, guys, one more comment. You see this X, Y, and Z? You see what happens as you do your EROs? Yeah, they change a little bit, but does it really matter what they change to? I would say not. The point is that these are just alphabet soup expressions with those same letters in them. And in fact, it doesn't even matter what they are. What you can do, don't change your notes right now, guys. We'll do this on the next example. Instead of writing X, Y, Z here, just write number symbol, number symbol, number symbol right from the very beginning. And when you do this ERO, it's just going to be the same thing because the numbers are just changing, but it's still got X, Y, and Z in it. And this is just number symbol, number symbol, number symbol. Now, what you have to interpret is that if you get a scenario with 0, 0, 0 number symbol, that's your pivot. It's actually going to be something that has X, Y, and Z in it. And if that pivot is way over in the far right column, no solutions, and you don't have a spanning set. Okay, I'll probably have you watch another example over the weekend. I'll make a nice little video, maybe with polynomials or something, and let you see another illustration of it. But thank you so much for being here today, guys, and I will see you next time.
If you look at